So welcome to complex analysis. We're essentially studying how you can do calculus over the complex numbers. That's sort of the big picture of what goes on in here. So the first thing we want to talk about is the complex number system. Now, so I've posted my notes in course content, and there's some useful things. Like on page 2, I have a table of symbols and the meaning. The other thing to keep in mind as you're using my notes is I use the, I write them in something called LaTeX, right, which is standard mathematical typesetting, and I use the hyperref package, which means that if you go to the table of contents in the PDF and you click on a section, it automatically takes you there. And if you're ever looking for something in my notes, you can do Alt-F and search for words. So while I don't have an index to my notes, it's in some sense better because you can, do a word search if you want. Of course, you can also email me anytime. I really don't mind. I will sometimes answer emails at absurd times, so don't be afraid to try. All right, so let's get started. Complex numbers. Where am I? Audric, you'll be pleased to hear the math department is now supplying us Hagorama chalk.
Oh, yeah. I was the first person in the
First person who what? Oh, is that right?
They have my box in there too, so I'm pretty sure they're inadvertent, but it's a chalk as well.
I see. So what are complex numbers? What are their properties? How should we think about them? So we're going to say the complex numbers are a set with the form x plus iy, such that x and y are real numbers, and I squared is equal to -1. All right. This is, at the moment, a formal definition of complex numbers because I'm not really telling you what I is. All right. I'm just saying there's this thing called I, and its square is -1. Right. So right away, that's a hint that I is not a real number, right? Because there's no real number that squares to -1, right? So there's something unreal, if you will, about this set to start with. Now, definition, if we have a plus ib times c plus id, that's going to be ac minus bd plus I times AD plus BC. Now, I say that's a definition, but it's also just what you would calculate if you were to, say, multiply these two numbers out and assume that the distributive property holds and that I squared is -1, right? Like, if you just multiply those out, so if we have A plus IB times C plus ID, we got A times C plus ID, right? Plus IB, C plus ID, which is AC plus IAD. So I'm assuming that the real numbers commute with I. See? And then when you group the terms with I, and you use, say, I squared is -1, right? So this gives us AC minus BD, plus I times AD minus BD. So all I'm saying here is that this definition is actually equivalent to the assumption that the distributive properties hold, I commutes with the real numbers, and the rule I squared is -1. So what are the properties? What are the properties of complex number addition and multiplication? Well, properties. So if Z1, Z2, and W are complex numbers, then we have a few things. First of all, they commute, right? There is a distributive property. So if I have Z1 plus Z2 times W, Z1W plus Z2W. So we have a distributive property. Of course, other things you already know, like addition also commutes. Z1 plus Z2 is equal to Z2 plus Z1, right? Although, admittedly, I haven't actually defined addition of complex numbers yet, have I? How would you add complex numbers? What's the assumption I'm working with? I guess I'll back here, right? Remark. So if we have A plus IB plus C plus ID, how do you add them? You add A to C, you add B to D. Just like that. So at this point, I should really introduce some terminology to fuel what we're doing. Now, I've stated both of these definitions carefully in the notes as definition 1.12 on page 1, all right? And let me finish these properties here. The other properties are associativity, and associativity. What do I mean by associativity? I mean, it doesn't matter which order you multiply them in, right? So I can put parentheses like this, see? Or I can put the parentheses like that. It's the same, whether we multiply the last two first and then multiply by the first, or if we multiply the first two first and then multiply by the last. And the same for addition. All right, so not really telling you anything terribly surprising here so far. All right, basically complex numbers behave like real numbers with respect to their algebraic structure. Let's see here. So I need to make here's a convention. If we write x plus iy equals to, z in the complex numbers, then we assume x and y are real numbers. All right. So if I say something like take a complex number, write it as x plus iy, or if I say a plus ib, I'm going to work under the assumption that x and y are real numbers and that a and b are real numbers. All right. This is to free us from writing this sentence over and over and over again, x and y are real numbers. Yeah. If I want x and y to be complex numbers, I will say so, all right? And I mean genuinely complex numbers. Technically, every real number is a complex number with a special form, right? So, definition, if z in the complex numbers has z equals to x plus iy, then the real part of z is x, and the imaginary part of z is equal to y. So both the real and the imaginary parts, right, are real numbers, right? I repeat, the imaginary part of a complex number is itself a real number, right? Now, so let me not be accused of not putting, excuse me, any numbers into this talk. So let's see here. How about example? Ooh, I forgot the red chalk. Really, the only color that shows up in here worth anything is the white, unfortunately. So for example, if z is equal to 3 plus 2i, then the real part of z is 3, and the imaginary part of z is 2, right? Any questions so far? No. So every complex number has a real and imaginary part. They could be 0, one or the other, right? Now, I should warn you, as you look at your first homework, which is what I call mission 1, right? That's due next Monday, except that it's not because next Monday is Martin Luther King Day, so there's that. But next Wednesday, it's due. And so in the homework, like problem 3, I have this funny looking RE thing here. I'll walk back and show you. See, this is how the typesetting of real ends up sometimes in the book and in my notes. That's the same RE. It's just I can't draw that fracture RE worth anything in my chalkboard work. It's one of my current things I need to grow, learn how to do chalk, the funny looking, yeah. But that is the same thing I'm talking about at the moment. Okay, so next definition, complex conjugate. If z equals to x plus iy, then z bar is x minus iy. This is the so-called complex conjugate of z. Now's as good a time as any to start talking about how we visualize the complex number system, right? How do we visualize the complex number system? We use what's called the complex plane, right? So like here, z equal to x plus iy, we can identify with the point x comma y in our usual Cartesian coordinate system talk, all right? And so, you know, this is the imaginary axis, this is the real axis, and if that's z, right, if z is up here, where is z conjugate? It's got the same real coordinate, right, but the imaginary coordinate is minus whatever it was. So complex conjugation takes your complex number and it flips it over the x-axis, reflects it over the x-axis. So down here is your z bar, all right? So that's complex conjugation, all right? What are the properties of complex conjugation? So if we take z plus w, we take the complex conjugate of that, right? So that turns out it's z conjugate plus w conjugate. All right. If we have z times w and we conjugate that, it's actually equal to the product of the conjugates. Let me prove the last assertion for you, all right? Let me prove number 2 here. Actually, there's a third one I should state before I prove 2. The third one is that, oh, no, sorry, getting ahead of myself. So, proof 2. I'll let you guys work out one for yourself. But for 2, if z is x plus iy, let me say z is equal to a plus ib, right? And w is equal to c plus id. Well, as we discussed, zw is, what is it? It's ac minus bd plus I times bc plus ad. I mean, you could write the ad first or the bc first. Addition commutes, right? So that's the product of z and w. What is its conjugate? So from this, the conjugate is ac minus bd minus I times bc plus ad. Okay, there's the complex conjugate of the product. Let's call that 1. So likewise, consider z bar, w bar would be what? That would be a minus ib times c minus id. Now we can multiply that out. When we multiply that out, what do we get? We get AC minus I squared BD plus I times BD plus AC, actually. Because minus a minus gives me a plus on the BD term. And BD, wait a minute, one moment. Oh, I can't do math. Try that again. Multiply that out, we get minus BC minus AD. There we go. Now, the I squared is minus 1, right? So minus I squared is 1. So we get AC plus BD minus, I'll factor the minus out, BC plus AD. I'll call that 2. So now compare 1 and 2. What do you got? Right, if we look at 1 and we look at 2, they're equal, right? So we've met in the middle. Therefore, 2 follows the z bar. The product, the conjugate of z times w is equal to the conjugate of z times the conjugate of w. Okay. We should talk a bit about geometry. Particular distance. So if I have z here, x plus iy, and I ask the question, how far is it from the complex, the origin? What's the answer? Uh-huh. Right, so this length is x, this length is y. So if we call the modulus of z, or the length of z, that's going to be the square root of x squared plus y squared. So this is the length, or modulus of z. Sometimes also called the absolute value of z. I tend to not use that terminology. I like to say it's the length of the complex number. But something interesting happens, right? The length of the complex number is related to the complex conjugate in the following way. Observation. Z times z conjugate is equal to x plus iy times x minus iy. But what's that equal to? Well, we have x squared minus ixy plus iyx minus I squared y squared. And of course, the cross terms in the middle there, they cancel out, and what are we left with? X squared plus y squared, which is what? Right, it's the length of the modulus, or the length of the complex number squared. So this gives us a wonderful theory. Some people would use this as the definition, all right? So what we find is that the modulus of z is actually equal to the square root of z bar. Which is, in and of itself, just kind of like, okay, well, that's kind of neat. But it's actually really profound when you appreciate what its implication is. So, what does this get us? So the question we can then ask is, what does the complex number multiplication mean, right? So, what does z times w mean geometrically? What can we say about that? Well, one of the things we can say immediately is we can say something about its length, right? What's the length of z times w? The length of z times w, right, is what? It's equal to the square root of ZW times ZW conjugate, right? The product of ZW with its conjugate. By the way, that's an ordinary garden variety real square root, right? Because we know that the product of Z and Z bar is x squared plus y squared, which is manifestly real, right? So what can you do? Well, we know properties of conjugate, right? We just proved over there number 2. So this is the square root of ZW, Z bar W bar. But what else do we know? We know that complex multiplication commutes, right? So I can move the Z and the Z bar around, and I can rewrite this as the square root of Z bar, W bar. But then I can use properties of square roots, because see, that's the square root of Z bar times the square root of W bar. But what's that? Well, the square root of Z bar is the length of Z. The square root of W bar is the length of W. So what we have now shown algebraically is that the length of the product of two complex numbers is the product of the lengths of the complex numbers multiplied. It's kind of neat. It's also not new in some sense, because that was also true for real numbers. If you take minus 3 times minus 7, you multiply them, you get 21, right? Well, you see the words. If you take minus 3 times 7, you get minus 21, right? So what's the significance of 21 geometrically? Well, if you take the distance of minus 3 on the number line and the distance from 0 to 7 on the number line, and you multiply those distances, that's 3 times 7 is 21. The absolute value of minus 21 is 21. So this is also true for real numbers with respect to absolute value. But it's interesting. Now, we haven't completely answered this question yet, because to really understand geometrically what complex number multiplication means, we need to look at a discussion of like the polar angle with respect to the complex plane, all right? But before I get too carried away here, make sure I'm not missing anything.
You did make a mistake.
I made a mistake. Oh no. Tell me where.
Just really early on.
Oh.
We had AD minus BD.
AD
On the last line.
minus BD. Oh, yes, thank you. Let me.
I didn't want to ruin your flow.
Thanks, Audric. Although I think whether or not I have flow is debatable. But here we go. Make a correction no one can see. So it's supposed to be plus BD. You guys can barely see that, but in the video it's like I did nothing. This blue is like,
Supposed to be plus BC.
oh, and still C. All right, thank you. Yes, that is a good thing. Yeah, you got to stop me if I do that kind of thing. Thank you. Now, it should probably be mentioned that you can also get well, let me erase some stuff here. So complex numbers, we can think of them as the plane, right, as a two-dimensional plane. And if we do that, then you can think about a complex number either as a point in 2 dimensions, or you can think of it as a vector from the origin, right? Just like when we think about points in the plane, we can either think of them as, well, points, or we can think about them as vectors from the origin, right? And if we do think about them as vectors from the origin, then we can think about their dot product. Remember, you've had Calc 3, right? Jade, did you have Calc 3? Okay, good. So, like if you say that this is the dot product, if you will. So this would be like, Z1 W1 plus Z2 W2, then where Z is Z1 plus IZ2, W is W1 plus IW2. So if you want, there's a formula for the dot product of the two two-dimensional vectors in terms of the product of Z and W bar. It's the real part of ZW bar. So I'll just leave that as a comment, all right? I won't work that out here. I think you have a homework that's basically about exploring that formula. All right. Now, there are other properties of the length. I should mention the properties of length. So we showed the big one, that the product of Z times W is the product of Z times the product of W. That's a big one, right? But another equally important thing is that if we take the absolute value, if we take the length of the sum, it's less than or equal to the sum of the length. This is the so-called triangle inequality, right? That's also true for the length of vectors in the plane, or 3 dimensions for that matter. Now, if we check this out, if we take Z, suppose we start with the absolute value of Z, right? Excuse me, length of Z, and then we say, well, that's equal to the length of Z plus W minus W, right? You guys agree? I just added 0. Then if I apply the triangle inequality to that, I could do that, right? So I could look at it as like, well, I'm going to take this and that. So this is less than or equal to the absolute value, excuse me, the length of Z plus W plus the length of minus W. It's easy to see that the length of minus W is equal to the length of W. So this gives us then that the length of Z minus the length of W, right, is less than or equal to the length of Z plus W. And it follows that minus the length of Z minus the length of W is less than or equal to the length of Z plus W, is less than or equal to the length of, well, this is actually not length, this is absolute value. The absolute value of, because this is a real number, so either this is a negative number or a positive number, right? So minus the absolute value of that has to be less than this, right? And the so that follows. And then, so what does this give us? This gives us that oh, I'm an idiot. I shouldn't have put that on the other side. I'm sorry, guys. It's one of my blind spots in this course. All right, I fixed it. Sorry, that wasn't there. This is true. And what does that tell you? Well, if you multiply that by minus 1, what does it get you? It gets you that the absolute value, excuse me, the length of Z plus W is greater than or equal to the absolute value of the length of Z minus the length of W. So there you go. That's very useful. This right here is very useful for certain arguments later. We use both the triangle inequality and this inequality for making bounds. Let me show you how that's useful before I go on. It's like, well, it's not, excuse me, it's not really an example, it's more of a comment. If the absolute value of Z plus W, excuse me, the length of z plus w. Oh, well, I'm having trouble not saying absolute value when I don't want to. Then 1 over the length of z plus w, right, is less than or equal to 1 over the length of z minus the length of w, right, for length of z not equal to the length of w, of course, right? That would give us 0. We can't divide by 0. That's still true here. All right? So this is useful because it gives us a way to bound reciprocals. Later in the course, we use this a lot to find a bound for things. This is inequality right here. All right. What else can I tell you about the length? The other important thing to know about length is that another property. So I guess I should say this is property 1, property 2. I'll call this property 3. So property 4 is that the length of z is equal to 0 if and only if z is equal to 0. The only complex number with length 0 is 0 itself. All right? That's an important property to know. Okay, so so far we've talked about the basic algebraic properties of complex numbers, the complex conjugate, how that allows you to calculate the length of complex numbers, right? So the next thing up to talk about is when can we find sort of the reciprocal or the multiplicative inverse of a complex number? So this is a question. So if z is not equal to 0, can we find w such that z times w is equal to 1, right? So, because then that would make w, we would want to call w 1 over z in that case, all right? So here's my derivation, if you will. And so this is not really a proof. This is a sketchy sketch. You should be very suspicious of the calculation I'm about to do. But here it is. If CW is 1, right, then W should be equal to 1 over Z, right? And that should be equal to Z bar over ZZ bar. Right? So if Z is equal to X plus IY with, not equal to 0, then perhaps Z inverse should be equal to, Z bar over ZZ bar, right? Which would be X minus IY over X squared plus Y squared. This is not a proof. I'm just exploring what a reasonable formula for the inverse of the complex number should be. How do we prove it works? Take a plus IB. You're thinking of doing an example with numbers in it? I mean, we'll do that. We'll do that. But to prove it, we just check the formula, see if it works. So here's my theorem. If Z is equal to X plus IY, which is not equal to 0, then Z inverse with Z inverse equal to 1 is given by And so here's the proof, z times z inverse is equal to x plus iy times x minus iy over x squared plus y squared, which is 1 over x squared plus y squared times x plus iy times x minus iy. So here I used, I guess I used a lemma technically. I mean, my lemma that I just used is that x minus iy over x squared plus y squared is x over x squared plus y squared minus iy over x squared plus y squared, which is 1 over x squared plus y squared times x minus iy. To be fussy, I mean, anyway, I should prove the distributive property for complex numbers to really make this totally rigorous, but anyway, it's true. And what happens when you multiply that? Well, you've got 1 over x squared plus y squared times x squared plus y squared, yeah? Which, of course, is 1, since the modulus of z squared is x squared plus y squared, which is not equal to 0 by property 4. Listen, I actually don't particularly like the way I just proved it. I think it's more elegant, and it's better to prove it using complex notation, right? What would the proof of this assertion look like in complex notation? This is one of the things you have to think about as you're struggling with a particular problem here is what's the right choice of notation? Sometimes a real notation, like I just used there, is cumbersome, whereas a complex notation is far more elegant. So here, this would be z times z bar over z bar, yeah? Which then would be 1 over z bar times z bar, which would be 1, right? Because that's 1 over the length of z squared times the length of z squared, which is 1, yeah? My point in getting to this step, Audric, is that I'm not assuming the thing I'm trying to prove. So these are real numbers that non-zero real numbers cancel to give me 1, right? So if I saw a student just cancel them here, I might be like, eh. If you had a comment that said, I'm canceling these real numbers, okay. I'm being fussy here, but...
No, but I see, because like the z just cancels out immediately if like you did it that slot way, then you're just left with z bar over z bar.
Yeah, right. So if you move the z around and you just cancel z with z and z bar with z bar, you're assuming what you're trying to prove, which here is that there is an inverse multiplicatively of the complex number. Right? So what we've shown anyway, whether you like proof 1 or proof 2, is that any non-zero complex number has a multiplicative inverse. So, we need to have language about how to ask questions in here, right? So one of the questions that we often like to ask is to, put a particular expression into its Cartesian form. So to put an answer in Cartesian form means to put it in the form x plus iy, right? So let's find the Cartesian form of z inverse for an example or two here. So example 1, if we had z is equal to, say, 2 plus 3i, then z inverse is equal to z bar over z bar, which is going to be 2 minus 3i over 2 plus 3i times 2 minus 3i. I mean, I don't really need to write it out. I should know after a bit in here that that's 2 minus 3i divided by length squared. So length squared is 4 plus 9. In other words, z inverse is 2/13 minus I times 3/13. Fine. Let me be really super picky here for a second. So this right here is the Cartesian form. So Cartesian forms means we write in the form a plus iv, where any of the i's appear like additively in the numerator. Like you can't have plus I in the denominator or something, you know. Once you have it in Cartesian form, you should be able to read the real and imaginary parts explicitly off, right? Like real part of z inverse here is 2/13. The imaginary part of z inverse is minus 3/13. Of course, you don't have to make it complicated. Like, once we know that the inverse exists, you can also just calculate reciprocals just using kind of common sense approach as well. For example, I squared is minus 1, right? By definition, I squared is minus 1. So that means that I times I is minus 1. So what's this mean? This means that 1 over I, so I can also say minus I times minus I is 1, right? So minus I is equal to 1 over I. And 1 over I is another notation for I inverse, all right? So apparently, the multiplicative inverse of the imaginary unit is minus itself. The first time I learned this, I was like, what? It's just such a weird thing, right? But there it is. All right. All right. So definition, Cx is going to be the complex numbers with 0 removed. This is like geometrically, basically take the complex plane, right? And you just take 0 out of it, right? Delete it 0. So this is the so-called punctured plane. Every complex number in the punctured plane has a multiplicative inverse, all right? Because we just proved that. What else can we say? Well, there are formulas for the real and imaginary part in terms of x and y. So another thing we should be aware of. I should have really done this earlier. My bad, guys. So z is x plus iy. Z bar is x minus iy. So if I add these equations, what do I get? Yeah, z plus z bar is 2x from addition, right? What happens if I subtract? I get z minus z bar minus 2iy, right? So this tells me that that x, which by the way is called the real part of z, is 1/2 z plus z bar. And this says that y, which by the way is also called the imaginary part of z, is equal to 1 over 2i times z minus z bar. So these are important formulas for us to know. They allow us to like calculate the real part or the imaginary part just using complex conjugate notation. Those are super useful. Okay, so what else can we say about complex numbers? Probably the most famous thing to talk about is just the application of the complex numbers to, like solving the quadratic equation, right? So I'll talk more about that in a future lecture where I've got a little bit more time to kind of unfold it. But just, long story short, and I explain this on page 4 to 5, over the complex numbers, polynomials always factor, right? This is the beautiful thing about complex numbers, is that they're algebraically complete. Like when we're factoring over the real numbers, we may or may not be able to actually factor a polynomial, right? But when we're working with complex numbers, we can always factor. Okay, so I would be remiss if I didn't talk about the sort of giant elephant in the room here, which is, what are complex numbers, right? So in the notes, I give you 3 different plausible explanations for what they could be. And those 3 models, if you will, for the complex numbers that I share in the notes may or may not make sense to you, depending on how much abstract algebra you've had. All right, so I'll just put them up here and talk about it briefly, because we're almost out of time here. But so model 1, and this is probably due to Gauss. Some people say it's due to Argonne, whatever. I don't really care who it's actually due to. But this is from like early 1900s. And it's just to say, well, you can take the plane, and you take A comma B and C comma D, and you say definition, this is equal to, you know, AC minus BD, comma, AD plus BC. Got it right this time, Audric. Haha. And that's the definition of this multiplication on the plane. And then with respect to this notation, you can show that basically 1 comma 0 is like 1, and 0 comma 1 is like I. Like, for example, you can calculate 0, 1 star 0, 1. It actually works out to minus 1, 0. All right? So you could just say that's how complex multiplication is defined. You could give that as a definition. You can prove all those properties I stated at the start, distributive, associative, commutative, all that stuff can be proved starting with this definition. And those are good homework problems. That's one possibility. All right? Model 2, it says that, so model 1 basically is A plus IB is equal to A comma B, if you will. Right? Notice that model 1, it naturally fits together with the pictures I've been drawing today in the complex plane, right? So actually model 1 is the model we're going to adopt. When I talk about complex numbers, I am literally thinking about a pair of real numbers, all right? But I would be remiss if I didn't admit to you that you could also construct complex numbers like this. You could say that they're 2 by 2 real matrices of this form. If you look at all 2 by 2 real matrices of that form, those also give you the structure of the complex numbers. Here, the identity matrix is like 1, and the off diagonal 1, 0, 1, minus 1, 0 serves like I. For example, you can check that I squared So that's the way the imaginary unit gets built into that model. All right. A third way of doing this, if you've had abstract algebra, is to take polynomials over the reals and quotient by the ideal generated by x squared plus 1. If you haven't had that kind of abstract algebra, don't worry about it. It's just a fancy way of saying you can invent this formal thing called x and force x squared plus 1 to be 0 in this formal setting. So this is a third way. In fact, I think a lot of people probably would take the third way as the way. Anyway, all 3 of these models, they all have real numbers and imaginary numbers that are separate, independent. They all have some unit in them that squares to be minus 1, where 1 is the multiplicative identity of the model. And they all have an addition and a multiplication, which have the distributive, commutative properties that we like. So logically, you could take any one of these 3 to be the complex number system. But I think a more mature viewpoint is to say complex number systems, what a complex system of complex numbers is just some set which has properties as we've discussed today, right? But for logical convenience, we are going to assume that our complex numbers are just the plane. So Anyway, that's it for today. Thank you for coming.